So today we are going to start with electric fields, and this is my favorite topic actually out of all topics because it's very similar to gravitational fields actually. So let's look at it. So first of all, there was once, electric field was half in AS and half in A2, and now it's complete in A2. So we also need to do the part about AS. So first of all, we are going to write the definition of an electric field. Electric field basically is a region where a charge feels a force or feels force. Okay. Now this force could be of two types. It could be attraction and it could be repulsion. Unlike gravitational field where it was only attraction. Now when you look at an electric field really, so when you look at in fact a charge, so basically charge could be either positive or it could be negative. Two different charges. So a positive charge will have field coming out of it, and it seems like it's coming through a single point, which makes it basically we call this as a point charge because it seems like that the field is coming from a single source or single point within. So this is the positive one, and for the negative one the field would always be directed towards just one single point. It's not coming out, it's going in like that. They can also ask you to draw the fields, so you should be aware of that. Like that. Okay, so this is a negative point charge. Now basically the lines you see, this is not exactly the field. The field is generally radial around it, so this pink line basically shows the field, but the lines basically have a certain meaning. So we're going to write electric field lines and their meaning. So electric field lines basically depict the direction of force on a unit positive charge, and that's very important to understand because a positive charge would basically mean that it's basically is attracted towards negative. That's why the field lines are basically towards the negative, and the positive charge is repelled by the positive charge, which means that the lines are going out of it. Do you guys understand what I'm saying?
Sir, could you repeat?
Yes, yes. I'm saying the lines depict the direction of force on a positive unit charge. So you know that a positive repels a positive, right? You've done it in O levels.
Yes, sir.
So you see if I put a positive charge right here, where would it go? Away from it, right?
Yes.
So this is what the line is depicting, that if you put a positive charge, it will go away here. Understood?
Okay, sir.
If you put a positive charge here, because it gets attracted to the negative, so basically the line is going like that. Understood?
Yes, sir.
This is the reason we draw lines like this. It is not a random thought, it has a meaning to it, and that's what I wanted to tell you. Now, so every field has a strength. Strength means that how much force it is putting on a certain type of object. So we're going to first define electric field strength. Electric field strength is basically of force per unit charge but this charge you just need to take it as positive. The thing is that it's just a convention that we write. In fact, let's just write, you don't forget it, so let's write positive unit positive charge. So basically that's why this is a convention. We gotta take this definition for life. The symbol for electric field strength is capital E. The SI units for electric field strength, because it is force per unit charge, so newtons per coulomb. Is it clear? And this is a vector quantity, which means it has a magnitude plus it is direction specific, so you have to be very, very careful. So electric field strength formula is written as E equals to F upon Q, where this basically means electric field strength, this is the force, and this is the unit charge. Is it clear, everybody? All right. Before we head forward, we would like to talk about something called uniform electric field. So a uniform electric field can only be generated between two parallel plates. What I mean by this is, suppose you got a plate which is connected to a positive supply, and then you got a plate which is connected to a negative supply. Is it clear, everybody? So basically, this would mean that in these parallel plates, the field will be like positive to negative, just like that. Now it really depends on how strong the field is, but we'll be going to talk about that in a bit. And at the edges, it is curved for a reason that I'm gonna tell you in a bit. Like this. So this is basically the uniform field. Now, when you're talking about a uniform field, basically it actually means that features. Number one, all lines are straight. Number two, they are equally spaced. And a uniform field will basically have constant electric field strength E at all points within it. Is it clear, everybody? Any questions here? Okay. Now, why am I drawing, field like this? It could be like, other types. Like, for example, I'll just show you. So let's suppose if a charge is positive like this, and there is a plate right here. So how would we make the field? Or there is a, sorry, I need to make a skewed line. There is a plate like this, and plate like this. So how would it be different? So let's see. Remember, just write a note here. The field lines always enter or exit the surface at 90 degrees to it. Now this has a meaning, which means if I zoom this, basically you can write it first and then I'll show you what it means. Done, everybody? Okay, let me see. Rafi, how are you? Nashmia?
Good, sir. How are you?
Nashmia, how are you?
I'm good, sir.
Nashmia, I used to call you Nashima all the time. And then I met Sir Numan, and he told me that you get really angry when somebody calls you Nashima. Is that correct?
Yes, sir. Most of this people just spell my name.
Okay. So I was like, oh no, let's call her Nashmia. So I read your spelling. I was like, wow, I've been wrong all the time. So
Yeah,
now, okay.
it's Nashmia.
Okay, that's cool. Now let's check this out. Okay. If you look at this, this is a circle, right? So from this very point, you got to make a straight line because it comes out like tangent to the circle, so it has to be 90 and it has to go in 90. From this point, it would basically come out like this and then enter straight. Do you guys understand? 90 and 90. Same goes 90 and then enter straight. From here, out from 90 degree and in from 90 degree as well. Understood, everybody? And the reason, why in the previous drawing I made curved lines at the end, because if you notice, this is the edge. Edge means this has to be 90 degrees, so it needs to go in and go out and in from 90. That's why. Do you guys understand this? Same goes for this one, where this will enter, exit at 90. But as the field, basically as the plates will be like going, like they have greater distance, you might realize that the gap between the field is also getting bigger. So it will be like, if this is positive, this is negative, so this is like this. Oh, I did not make it, sorry. Like this, like this, like this, like this. Okay. All right. Everybody understands this, right? Any questions? Please let me know. Okay. Now, so what you're going to learn from this is, number one, the strength of electric field depends on how close the lines are to each other, which means that this section that you see right here has a greater strength than this section because the lines are far away from each other. Everybody understands this? Now, so before we go further, I just want to, explain a few more things. And one of those things is that the derivation of acceleration in an electric field. And this is so important. So we know that if there is one force acting, so electric field strength is given by force per unit charge, and force is given by mass times acceleration. So these are the two formulas we know. So we can write this as F equals to E times Q, and this says F equals to ma. So we can equate these two. So EQ will be equal to ma. So A will be equal to EQ upon m, and that's a simple one. So here again, this is electric field strength, this is the charge, and this is the mass, and of course this is the acceleration. Any questions? Please let me know. Okay. All right. Have you guys written it? Should I move on?
2 seconds.
Okay.
Done.
Great. Now, so first of all, there are a couple of things that I want to tell you. This is prereq for any basically chapter. It was also in AS, I believe. I believe you guys have done it already, but it's fine. So 1U is basically the unified atomic mass, which is equal to 1.66 times 10 raised to power minus 27 kg. It's also given in the...
Wait, say,
Sorry?
the heading above acceleration, is there only 1 point in it up? Strength of electric field.
I don't understand. What do you say?
Above this, you wrote the heading, strength of electric field depends on, and only 1 point.
Yeah, it basically depends on how close Basically, I should have written it. Wanted to write another thing, but I thought maybe I'll do it again in the next part. Strength of magnetic field um, is depicted by. Let's write this, okay? Depends on one more thing actually too. So. Okay, now. So, one E is considered to be the elementary charge, and elementary charge is 1.6 times 10 raised to minus 19 coulombs. You should know this too. It's also given. But the point is that why am I doing this right now? Oh, by the way, yeah, one more thing. A lot of time they will also use massive electron. So that's also given, by the way. But it's good to remember, 9.11 times 10 raised to or minus 31 kilograms. Okay, now. So whenever you have any, say, so in 10 minutes, please rejoin. So whenever you have like, suppose something like helium, and they have given you 4 and 4 and 2. Basically this 4 and 2, let me write it bigger actually, just to explain you better. This 4 basically means that it has a mass of 4u and the charge of 2e. So if you want to find its total mass, so the mass in kg would be equal to 4 times 1.66 times 10 raised to minus 27. That comes out to be 6.64 times 10 raised to minus 27 kilograms. And the charge in coulombs will be 2 times 1.6 times 10 raised to minus 19. So that should come out as 3.2 times 10 raised to minus 19 coulombs. Is it clear, everybody? So you can basically change this like that. Okay. Fine. Now let's go forward. So now let's see that how do we analyze uniform electric field before we go to non-uniform electric field. So let's do that. Let me just copy this because I would need this again. Okay. Hello. Walaikum Assalam. ठीक ठाक. नहीं अभी तक नहीं. हाँ चलो वो बताएगा फिर तो क्या. ठीक है. Okay. All right. Now. So when you're looking at a uniform field like this, as a matter of fact, so there will be certain key features that you need to remember. So let's suppose this was like plus 20 volts and this was negative 20 volts, right? So there is a voltage, and the distance between here till here, it is given as 8 centimeter, right? Okay, so basically you need this, and for that, first of all, you should remember that we need to find the potential difference. Let me use another color. The potential difference across these two plates. Now, potential difference is a scalar quantity. which means whenever you're going to find difference, you will always do bigger value minus the smaller value, not the opposite. So which means that potential difference is going to be plus 20 is a bigger value minus 20. So it is going to be 40 volts. Is it clear, everybody?
Yes.
Now the next thing. In O levels, you might have learned about voltage, and you might have learned this definition that voltage is basically the work done per unit charge. Do you guys remember this?
Yes, sir.
So we can write this as voltage equals to work done upon charge. Now this is very important. Let's see. Now what I can do is that I can basically write work done as force times the distance over the charge, because work done is essentially, force times the displacement. Distance is this d. Okay, so now if you look at this section, what do you see here? Have you seen anything as this? Do you know any quantity that says
Electric field strength.
electric field strength, right? So because electric field strength we just learned is force per unit charge, so we can replace this and we're going to get voltage equals to electric field strength times D. So electric field strength then will be voltage over D. So which means that there are two formulas, right? F upon Q and V upon D, where this formula, just remember, the SI units now could be either basically Newton per coulomb or volts per meter. Basically they have the same basic unit, so they define the same quantity, right? Now in this formula I just want to tell you that this particular thing is the change in potential, which is basically the voltage. This is the distance between plates. So this is how it relates, right? Now if I try to, because this is a uniform field, if I try to show you a graph, it would basically look like so we got electric field strength, we got voltage positive, voltage negative, we got D centimeters or meters, whatever it is, it doesn't really matter for that matter of fact, but right now I'm taking centimeter. So basically what it means is that if you look at the point just on this plate, so at this point the potential is equal to plus 20, and at this point the potential is equal to minus 20 after traveling the whole place, right? So what you're going to do, that you start from here, so it's plus 20, and then you got to reach minus 20, but it comes after 8 meters, which means that if you draw a straight line just like this, so right till the middle, which is basically the 4 centimeter mark, right in the middle, the potential will be 0, and right at after 8 centimeters the potential will be minus 20. Do you guys see this? Any questions? Now remember, this constant change shows uniform field, just like this. Okay, right. Okay, now the interesting thing here is that you might also see something very, very important, and that is if I try to find the gradient of this line, so I'm finding the gradient, right? So this place is like change in voltage, and this is the change in distance. So the gradient is basically defined as the change in voltage over change in distance, right? Everybody understands this?
Yes, sir.
Do you see on the screen any formula just like this? This is?
Eyes over.
No. Do you see any
The
formula?
electric field strength.
Yes. This is the electric field strength. But if you notice that the gradient is basically negative. Do you guys understand this? Because it is a downward slanting line, right?
Yeah.
So now we can actually call this as something. Okay. All right. So, well,
Well,
now, so basically, this is why electric field strength is sometimes called, also known as, right, the negative potential gradient, which means that if you take gradient of a potential and distance graph, it will show you electric field strength. Any questions?
So we will keep the value as negative or we gonna make it positive?
Uh, well, it will all automatically be like the same. Don't you worry, okay? It will be the same.
Okay, sir.
So the negative sign will cancel out automatically. You don't have to worry about it. It's just that you should know that it is the gradient of potential graph, but it is also negative because the line slants like this. Is it clear?
Yes, sir.
Okay, very good. Now, okay, you can please draw this. I've written so much today, huh? I'm like, wow. Wait. So now let's try a question. Okay, see if we can do that. Okay, so basically the question says, what will be the force on an electron when the electric field strength is 4.5 times 10 raised to power 5 volts per meter. Okay, so this is the first part. Then in the next part they say how fast the electron be traveling if it accelerates from rest to a speed v within 10 centimeter distance. Okay, so this is the next question, and the third one. Oh crap, wait a second, huh? Forgot about that too. All right, now the next question it says is that what would be the potential difference at 10 centimeter, assuming that it travels in a uniform field. Is it clear, everybody? Now let's try this, huh? So first of all, for the very first question, what will be the force? So we know that electric field strength is given by force per unit charge, and the charge on an electron is basically 1.6 times 10 raised to power minus 19 coulombs. This is the elementary charge. So F will be equal to 4.5 times 10 raised to 5 multiplied by 1.6 times 10 raised to minus 19. Is it clear, everybody? Now, so this comes out to be, this should be around, I think, 7.2 times 10 raised to power minus 14 newtons. Understood? Any questions? Now, Then it says how fast the electron be traveling if it accelerates from rest to speed v within 10 centimeter of distance. So we know that this velocity and constant acceleration are related by this equation 2as equals to v square minus u square. The initial speed was 0, so it means that this will be 2as equals to v square minus u square, which is 0. And now let's keep this equation right here, where we know that acceleration itself is equal to eq over m. You guys remember this? So we can write this equation as v square equals to 2 eq upon m times the displacement. So let's put in the values. 2 times 4.5 times 10 raised to 5 multiplied by 1.6 times 10 raised to minus 19 multiplied by the displacement, which was 10 centimeters. So I'm going to change that to meters. So this will be 0.10 meters, divided by the mass of the electron is 9.11 times 10 raised to minus 31. You can find these values in the sheet. Okay, because this was v squared, so we got to take under root on both sides, and ultimately you should be getting 1.26 times 10 raised to 8 meters per second. Any questions, please let me know. Okay, now so keeping that in mind, then let's move to the last one. Now because it is moving in uniform field, we got to find the potential difference. Do you guys know any formula related to that? Any formula? No way. That's not fair. Abhi to we did it, like E is
The field strength at a distance.
yes, the potential gradient, right? Okay. Now here I would like to tell you very important thing. Now if you put a negative sign, because the field basically is for positive charge particle, right? So the potential difference was basically we want to find that. So this will be minus EQ. So this is 4.5 times 10 raised to minus 19, because this is basically for a positive charge. Whether you put a negative sign or not doesn't matter, because then if you put a negative sign, you also need to put the negative charge value of the electron. So negative and negative will cancel out, which will give you something like
So 4.5 and 10 raised to 5 ether.
10 raised to, oh yeah, sorry, 5 tha. Alhamdulillah. Okay, so basically this will give you something like, I don't know, I gotta calculate this. This I haven't calculated yet.
7.2 into 10 raised to minus 24.
Volts. This is the answer. Okay.
Yes.
So this would
There's
be,
positive 5 or negative 5.
it was positive 5. So it would be less than
Then it's 10 raised to negative 14.
14. Okay. So this would be the voltage. Is it clear, everybody? So if you don't put a negative sign, it's fine, because then you can just put the elementary charge. It will give you the same answer. It doesn't really matter what you do. But the thing is that if you put a negative sign, then you have to also consider a positive sign with a proton and negative sign with a electron. So that's something to note here. Okay. All right. So I believe we are done with at least the AS part, which was the previous AS part, and probably tomorrow I guess we're gonna continue this. All right.